Welcome everyone to the class. Okay, so now we have to look at how to perform backpropagation in for this sort of an architecture. So what changes? See, math wise nothing changes because all we are looking at is multivariable chain rule. But what's important to note here is that when you have an architecture this way, suppose you are solving a classification task, which is this. Okay, where you are tapping the output at the output the last RNN cell, then the gradients have two paths, right? One is right to left, the other is top to bottom. Especially if you have multiple layers, the gradients corresponding to every hidden state and every variable that we are looking at here has two paths. Okay, see, one path is coming from right to left or left to right, the other path is coming from top to bottom. Okay, so yeah.
So what does the depth correspond to in RNNs? In CNN we know that it corresponds to different filters that we had, but in RNN what is the depth?
You can still see them as different features, right? Capturing different features at different depth level. It is simply having multiple neurons so that universal approximation theorem is obeyed, so that you have multiple parameters to cater for. You need to anyway do function approximation at the end of the day. You need to ensure that it happens that way. That is what the depth is. Yeah. So now the gradients corresponding to each of the parameter that we are looking at. Now we'll have two paths, right? One from right to left and top to bottom. So when you are doing backpropagation, you'll have to ensure that these gradients are taken care of. That's it. When you are adding the gradients, the paths that we are looking at. In an MLP, what happens is when we define the delta had only one path, right? The output to input. So it did not have the other path. Now we have two paths. Okay. So this algorithm where you have to just do backpropagation from two different directions is called backpropagation through time. Okay, it's called BPTT. I leave the algebra as an exercise, do that. So what's more important is this BPTT, this architecture leads to a particular degenerative problem in RNNs, which we will discuss in a while. But please look at the math of BPTT. It's the same as the backpropagation that we had done for an MLP, but you will have to ensure that when you apply that multivariable chain rule, you have to take both the directions into consideration. Okay, please work the math out. Okay, now give me a minute. Okay. So there are two things that's happening in an RNN, right? So one, the hidden state is maintained across time, okay, which is what is capturing the temporal information, and there is parameter sharing across time. It's happening. Because of this, so what might happen is, as the length of the input sequence increases, when you backpropagate from output to the input, okay, the gradients, the magnitude of the gradients depending upon the weight matrices or the singular values of the weight matrices will keep reducing. We'll see the math in a while. The idea is the following, right? I mean, if I have to roughly translate in an intuitive non-mathematical way, the longer the time elapses, the lesser our memory remembers, right? The lesser our memory can capture. If you look at these hidden state HT as a memory, okay, of that the recurrence, right, on the sequences is captured using the HT, which is the hidden state. The longer the sequence is, okay, the lesser is the influence of the past on the current hidden state, and that should come up in the math somehow. The way it comes up is as the magnitude of the gradients while you are doing backpropagation. See, what happens is, remember what backpropagation does, right? It's gradient descent at the end of the day. If the gradient of the empirical risk with respect to a particular parameter is very less, then that parameter will not get updated at all because the gradient is very low. Now we should not be ending up in a case where the gradients of the the empirical risk or the loss that we are computing will be very low as we progress longer in time, and that happens in an RNN by construction. Why? Because there are two things here. One, there is parameter sharing across time, which means that you are multiplying the same parameter every time across time, and there is all the information about the sequences is captured and embedded in the hidden state, which is recursive in nature. Okay, that is what is infamously referred to as the vanishing gradient problem in an RNN. We will see the math of what vanishing gradient problem is, and we will see what can be a respite to such a problem. But did you understand what is happening? Because of the recursive nature, the gradients as you accumulate over time will have lesser magnitude. We will see the math here. Okay. So, BPTT leads to vanishing gradients in long sequences. So, what is the math? So, at each time step t, we will look at vanishing gradients. So, at each time step, we have the following equation. So, Zt is W1 ht minus 1 plus W2 xt. I will leave the bias in a while for ease of algebra. We have ht to be equal to sigma times Zt. So, this is the current equation that we have, right. Suppose Lt be the loss at time t. Capital LT, L capital T, yeah, be the loss that we compute at the final time step. So, and we are computing the gradient at that. Let us say that we are looking at a classification problem here, and LT be the loss at time t. So, we have do LT by HT, where HT is the hidden state at some time point t, can be decomposed as right. Dou LT depends on HT through H capital T, isn't it? Come again. What should be XT? I mean, here this is not X2, this should be XT. This is what you are saying? Okay, yeah. So, is this clear? So, loss at the last time step, okay, the dependence of the loss at last time step on HT is through the last hidden state HT, right. Now, consider this particular term. The question that we are asking is, what is the dependence of the last hidden state, okay, on the previous hidden states of previous time? What is that? That is the product of all the Jacobian matrices or the derivatives is simply chain rule. So, what am I saying is, if you are considering a time step small t, okay, then the last hidden step depends on the penultimate hidden step, and the penultimate depends on the previous one, and everything till time t. It does not depend on anything that is prior to time t, because we are only looking at time t here, and that dependence can be written as a product of several Jacobians. And the reason I am saying Jacobian is all these are vectors, right, and we are looking at Jacobians here. Let me just write it this way. This is the product.
Go to capital T minus 1.
This is k equal to t to capital T minus 1, correct? Because k plus 1 is what I have written here, it's t minus 1. Is that all right? Yeah. Okay. Now consider the this particular Jacobian del hk plus 1 by del hk. We have hk plus 1 to be some sigma. See, look at this, hk plus 1 is sigma zk and zk is this. Okay, I will unroll it and write it this way. It is sigma w w1 or w2 w. Okay, let me write it, hold on. So this is hk plus x k plus 1 because it's hk plus 1. So what are these w's? This is 1 and 2. Okay, two different parameters, right? So this is how it is. Now if you look at the derivative of this, so now consider hk plus 1 derivative of this with respect to hk. If I write this would be, just I'll have done the algebra, take this is the diagonal of sigma dash, okay, that is evaluated at zk plus 1 times so w1, okay, where this diag is a diagonal matrix. So what I am taking, take a diagonal matrix and put sigma dash or the derivative of zk plus 1 in it to its diagonal and multiply it with w1. So that's the derivative. Okay, now typically what happens is, okay, let's look at the norm of this. Consider the norm of this particular vector, derivative, which is simply use the, okay, not this, let's look at this itself. We are interested in, sorry, made a mistake. So because we are finally interested in this derivative, right? Here we are looking at the derivative of the loss with respect to the hidden state. By the way, why am I even considering this term? I am considering this term because it appears in the backpropagation through time. See, finally we need to compute del LT by del W, del W1, and the dependence on LT or dependence of LT on W1 is through the hidden states, multivariable chain rule, and this term comes up in the backpropagation equations, and that's why we are looking at this term. That's why I asked you to actually write down the BPTT equation so that you see that this term comes up. This is very similar to the delta term that we looked at. Recall, I mean, in the MLP there was a delta term, right, which defines the error. So this term is very similar to that. Okay, the problem of vanishing gradient comes up because we have this sort of a term. Finally what we need is the gradient of the empirical risk with respect to W's, which depends on this through chain rule. Okay, anyway, so we need the norm of this particular term. Now we will use the Cauchy-Scott's inequality, and you have product of these many gradients here, right, and we computed this gradient as diag of this, and you have two terms here. So I will use the inequality and write that as this, still have this product. So this norm of this matrix diag sigma dash computed at zk plus 1 times norm of W1. Okay, huh? Inside what? Of course. Now see diag, or rather this one, the norm of diag, this is bounded. Okay, this is always bounded. Why? Sigmoid is between 0 and 1, right? Typically, if you take the sigmoid function or tan h or something, this norm is bounded. Okay, and now let use sigma already. What other symbol? Use lambda. Let lambda max be the largest singular value of W1. Okay, and we know that norm of W1 is lambda max, isn't it? The norm of a matrix is equal to the largest singular value, which means that this gradient now is upper bounded by, this is the first one is less than 1, right, and the second one is equal to lambda max, and we have t minus t of them, which means that this is bounded by lambda 1 to the power of t minus t. We have those many of them. Is that okay? See, this is a very nice result. Okay, so as the gap t minus t increases, lambda 1 power t minus t decays exponentially. Did I write? What did I write? Lambda? Yeah, no, it's lambda max. So that's it. So this is the vanishing gradient problem. As the length of the input sequence increases, okay, the gradients corresponding to the earlier time steps will be insignificant. Therefore, see, why do we care about this term? We care about this term because the dependence of the loss on the parameters is through this term. Okay. Now, if this term decays exponentially, then the loss or the gradient of the loss with respect to the parameters decays exponentially as the sequence length increases, and this is the infamous vanishing gradient problem. And if your lambda max is let us say greater than 1, then it is the other problem called the exploding gradients. Okay, both are dangerous. So that is why, see, when RNNs existed for a long time. I mean, an anecdote is my BTEC thesis was on RNNs. Had written BPTT and all that, used it for some small problem. But the thing is, they could not work for longer sequences because of the vanishing gradient problems. So something has to be done to solve this. So that's where we have the architectural tweaks that one would do with like GRUs and LSTMs that are constructed to solve this particular problem of vanishing gradients. Okay, so vanilla RNN has this particular problem. So why does this come? I mean, it's just because of calculus and multivariable calculus. Write down the gradients, you will see that the gradients are strictly upper bounded by some value that exponentially decays. That's it. Okay, any questions on this?
The backpropagation when you're updating the gradients, how do we ensure that all W's and this stay same?
See, that is through equations. No, hard code them.
Yes, but in different level horizontally, we are having different.
That's okay. See, that is why the dependence of your loss on the parameters will be through the hidden states. You need to add the gradients with respect to each of the hidden state while you are concluding. That is why you need that sum. So it's basically the loss or the empirical risk depends on the parameter through all the states at all times. You need to add all those gradients. That's exactly what BPTT is all about. Okay.
So we didn't want this stuff. We wanted to get HT with respect to W1 elements in W1. So this stuff says that when we take the linear combination across all the hidden states, the gradient with respect to some of the terms, it's like if we propagate this to the WTs, that would be 0. That would decrease. So this in some sense says that for the HTs that are closer to the last state, the W's there would not be 0.
Agreed. Sure. See, the observation that he is making is that this only says that the gradients vanishes exponentially as you go farther and farther from the outermost state. Agreed. But this is not only about the outermost state, right? Suppose you are doing a sequence to sequence task, the loss has to be computed at all time steps. At any given time step, as you move further in the time, the gradient decreases. That means that these W's will be learned, okay, by ignoring some of the time steps.
Earlier times.
Exactly. So if you ignore the earlier time steps, so your sequential model is not correct. See, today's models have a context lengths that run into millions of tokens, isn't it? And by the way, you might have heard this word token, right? Token is every time step. Every vector that we have in our sequence is what is called as token. And by the way, in natural languages, in today's state of the art models, it's not the word that is taken as the fundamental unit. It is a token. So what is a token? There are multiple tokenizers as well now. So one thing is this byte pair encoding tokenizer, where you start with characters as each tokens, and you combine characters that appear multiple times into one, and so on, run this algorithm iteratively to get tokens. So put all the tokens in what is called as a vocabulary, and today's vocabulary size is about millions of tokens, and a sequence is a combination of tokens, or rather, yeah, it's an ordinal set of a token. Whatever we have written as X is what is called as a token, right? So that's why you don't want this. No longer the sequence lengths, the gradients are vanished. You don't want that to happen. Sometimes you do. I mean, that's why basically the idea is the following. Sometimes you need to forget. Sometimes you should not forget. Now, wisdom is to understand what to forget, when to forget, and what not to forget. How does that translate to mathematically? You need some of the gradients to go to 0. You need some gradients not to go to 0. How do you do that? Just add an identity function. That's exactly what is done in the residual networks as well, right? That's what we will see. Now, mathematically speaking, what's happening is the dependence of H here, right? Let me show you that. Maybe I'll write that. So HT recursively depends on HT minus 1, right? All HT depends recursively on the previous hidden states. And that dependence is through this linear matrix W. Now, because of the presence of that W and their singular values, that the gradient is going to 0. Now, what if I also give a parallel path where instead of the recursive dependence being through W, I make the recursive dependence through identity, which means I have a path where HT is equal to some constant times HT minus 1. Then if I also have a scalar, HT is equal to some alpha times HT minus 1, by changing that alpha, I'm telling whether this has to be forgotten or to be remembered. Mathematically what happens is the gradient have two paths. One path where it is vanishing, the other path where it need not vanish. So that, in fact, the name is also, there's one modification to RNNs which is actually named as highway networks. Highway networks. Highway because there is a path from the output hidden state to the input hidden state without any multiplications of these W matrices. I'll write all the math right now. That's the idea. The classical idea in any linear dynamical systems is if you have a recurrent relationship between the variables in a system, when you are taking the gradient, if you want to break the recurrence, add identity to that. That's all. You can have thousands of architectures around this idea. I will show you a couple of them. Okay, so that will facilitate you forgetfulness. That will also facilitate you remembrance. Have both. So that let the network decide what to remember, when to remember, how much to remember. See, how much to remember comes as a learnable scale. What to remember comes as the matrices, and so on. So that's why some of the variables in this LSTM are actually called forget gate. They are called memory gate and cell state and all that because of this very reason. So I am not a big fan of calling them, I mean, making them non-mathematical and giving some non-existent biological intuitions. I will only write math now. You got the basic idea, right? Whenever there is a linear system which has a recurrence relationship through some linear transformation, if you apply chain rule through the recurrence, because of the depending upon the eigenvalues or the singular values of this recurrence matrix, the gradients will die down. To ensure that that will not happen, you will have to create a path that does not have multiplications with this matrix. That's the idea. Okay, let's look at it right now. Any questions here so far? Yeah.
Sir, can there be any regularizer that can ensure lambda max to be equal to 1?
Well, not because it's a good question. The question is, can there be explicit regularizers where you ensure that your lambda max is not
Equal to 1.
I'm not saying it's equal to 1, it can
Have it, then this will not be a problem.
oh, exactly equal to 1. Yeah, we will do that. We'll see that, in other words, what you are saying is, can I do an architectural change such that there exists a path where when would lambda max be equal to 1? Only when your matrix is identity, then your singular values are equal to 1. That's exactly what we will do now. It's nice that you asked that question. We will put a regularizer, architectural regularizer right now in such a way that we will have a path where lambda max is equal to 1. That's a nice way to look at it. How do you do that? If you only make it 1, there is nothing to learn, right? The dependency is only recurrent linear. We want a capability where we want some things to be forgotten as well. So we will have that sort of an architecture which we will see now. Other question? Yeah.
We initialize our W1 correctly, we can have a good control of the lambda max. But the other term that we have, which is the diagonal of sigma dash,
Yeah.
that is the thing that we can't control, and that should be our true goal.
See, here you cannot control it at all, no? Yeah. So what you can, you can only control this, because this Z here, the dependence of Z is also on W1 and W2, right? The recursion is coming from the Z only. See, if you look at it, those two terms, but for the sigma, they are exactly the same. This nonlinearity has to be there to ensure that the universal approximation capability. If I remove this, all this will become linear functions, no? And linear functions can only, we know that the linear discriminant functions have their limitations. Only by having the sigma you can approximate any function to arbitrary closeness.
But if we have a good lambda max, that is not greater than 20, but still the other term is exponentially decreasing.
That will happen. That you can't do anything about it. Yeah. It's similar thing, no? This happens even in an MLP. Whenever there is a sigma, this is going to happen. But here we can control, no, by making that lambda max equal to 1. Okay, so let's do that.
The exploding gradient can't be solved by
Why? Same thing. You have one, you still have that skip connection thing, Doesn't matter. In fact, you can normalize the values such that the exploding gradient becomes a vanishing gradient thing. It's just a matter of scale. Okay. We will stop here and continue in the next lecture.